So first and foremost, thank you everyone for giving me an opportunity to present my paper. My name is Pawankumar Sharma. I've been a researcher and a PhD student at the University of the Cumberlands, about to complete my dissertation. Uh, I also work as a staff product manager for Walmart in the Bay Area and focus on last mile delivery. This is a paper that I'm presenting. It's called Practical Applications to Prevent Cyber Attacks on Internet of Battlefield Things. And my other co-authors are Dr. Lotfollah Najjar from University of Nebraska, Omaha, as well as Dr. Sriram Srinivasan, and he's from the Virginia Commonwealth University. So the introduction part, what is my paper and what does it consist of? Technological advancement has led to the development of Internet of Things, providing the driving force for the technological development of the advanced smart devices that is exemplified by heterogeneous machines, sensors, and actuators. The devices exchange data using ubiquitous connections, enhanced situational awareness through real-time data transmission, and within the battlefield, situational awareness remains paramount for soldiers to enforce effective combat missions. The IoT has thus facilitated the Internet of Battlefield Things, popularly known as IoBT, through which it allows information dissemination relying on internet connectivity. However, the advancement in technology has provided terrorists an avenue for attacking the various security software exemplified by IoBT, hence vital to the combating capability and the situational awareness without the various coordinated battlefields through instituting the various combat capabilities. The stoic geometry and mathematical epidemiology constructs offer a foundation for the generic framework for reconfiguring the IoBT design networks for the constantly changing missions, and the cognitive connectivity framework forms models for adaptation to the network changes interconnecting the spatially dispersed smart devices, hence the remote deployment of IoBT. The model that I'm stressing will capture key nodes and edges within the deployed network. The model as developed also offer robust and cost adequate network infrastructure, and the information has a directional communication exemplified by the command and control node responsible for the node sensing and the generation of the operation command alongside transmission of the strike nodes. The information that is propagated within the nodes alongside transmitting the information directly, and the IoBT network security requires robust protection against edge removal attacks from network interconnection through malicious attack behaviors using meta-heuristic algorithms. So basically, there's a need to prevent the Internet of Battlefield thing security, which is vital in the times of war, and communication has to be very swift and adapt so that the right communication is passed through, and we are also able to provide security and information dissemination has to be done in the right manner. Now let's talk more about network geometry. The network geometry application within the battlefield includes the interconnection of various wireless interconnections, including armored vehicles, smart devices, and unmanned aerial vehicles. The various devices have their transmission monitored through transmission power correlating to the communication range within the uniform deployment density that is represented by, and say, R2, and denoted through delta M devices within the various kilometer ranges. It might be 1 kilometer, 2 or more. Then the incorporated devices have a communication range tunable within the interval of certain distance and limits, which has minimum and maximum values. The devices that are connected can subtract the homogeneous Poisson point process. So that's also called PPP within the intensity of a certain denoted through specific assumptions that every device has independent placement and the various other devices placed independently within a combined network form part of the PPP. So that's the overall network geometry that I have utilized, and this network geometry also represents the Euclidean distance whose communication between the various devices allow modeling using the random geometric graph within a connected radius. So everything that is within a connected radius has its own independent mechanism, and these devices are able to communicate within a war scheme. And the devices during Internet of Battlefield things are thus protected. The network exposition across different devices calls for decomposing the network layers, as each layer correlates to various devices that are interconnected and are communicating, of course. The intra-layer connectivity accounts for the connection between similar labeled things, while the interlayer translate to different things interconnection. Now, coming to the communication between various network models occurs through either an intra-layer or interlayer or a combined network interconnection. The intra-layer, of course, interconnection occurs within network layer, allowing the device communication. In case of their interconnection within a distance, the communication neighbor networks within devices have a standard reference. The RGG connectivity, which we call the basic connectivity model, comprises of devices as the device's degree defined through average device numbers with consequent devices noted within a framework or an architecture, and they represent a set cardinality. And also the interlayer connectivity involves the devices within single network layer communicating with various devices within interconnection layers as incorporated inside the influence region. Now, the influence region has a typical representation within each layer projected by circles, and the network-wide connectivity entails collapsing the essential dual network layers into a single virtual network to enforce the device connectivity, with the connectivity integrated into a degree. And the incorporated layers have the degree of interconnected devices, and they remain within the PPP distributed within the respective layers, and hence a combination of layer equating to the Poisson matrix distribution. And all these combined network connectivity means and entails that the complete network connection within a unique characteristic expressed as a combined network degree, wherein all the devices within this network have communication facilitated by the assumption that particular degree devices have their evaluation correlated to the accumulated device number of the type within an influence area. And the average total number, average total network degree has a distribution poised as the multimodal Poisson random variable. Now we come to the network model architecture, and basically you can see the IoBT network has a wireless connectivity with the most significant interlinked devices facilitating the directed network format. And the information that within IoBT requires each device to generate a data of its own and a propagation capability, so that it's able to communicate to the other interconnected devices. The information spread rate is also calculated with the help of a formula that is depicted there. And the various models that are existing across the Internet of Battlefields determine the threat levels, and they are also able to jam and use physical attacks and various attack models that are already in place. And sometimes these devices incorporated within IoBT might be able to fail to broadcast the information it has received the devices communication within a certain time slot. So for that, I use a heuristic algorithm that provides an efficient method of detecting the topology of strategically positioned nodes, facilitating the decrease in the size of the dominating set. And it also helps in measuring the identification of the node with the characteristic of the set. Now, there are various interconnected cross-layer connecting dominating set formation algorithm. We call it CCDS. So CCDS comprises the formulation alongside repetitive relayed node pruning, and each node has to gain the knowledge of the neighboring topology and the consequent CCDS topology, learning the connectivity of the various neighbors through mutuality of the various distributed protocols received from the various neighbor values. Now, the CDS formation consists of a source initiated relay node facilitated through constituent node execution with consequent division into tasks, neighbor prioritization, and architectural tasks. The consequent has the priority embedded in the neighborhood with the decreasing values of the CCDS that are part of the overall network. And there also exists progression selection of say one hop neighborhood, which is like, the neighboring node just next to the adjacent node. And there's also information flowing because of the inclusion of the relay node set with the most considerable index values covering the last node within say a two hop neighborhood. So there's one hop neighborhood, which is the node which is adjacent to a particular node. There is two hop neighborhood, which is one after the other node that is present. They do not have a direct correlation, but another node is present. So that's what we call a two hop neighborhood, as it is understood from the two hop neighborhood acronym itself. Now, we also look at the pruning phase that has a capability to relay node selection that culminates reducing various repetitive nodes and achieving the balance in effective and increased CCDS entails using the restricted pruning commands with the self-pruning model that is in place, making it an efficient mode in relay node set reduction compared to the various schemes for broadcast coverage. Now, the centralized CDS multi-layer networks using the fast CMDSM as the centralized algorithm. This algorithm possesses a unique character of multi-layer network topology embedded within the network aspects. And there are various other aspects to it. Something is called as MDS, or the minimum dominating set innovation, the CDS architecture, and the repetitive DS node pruning, consisting of the algorithm's essential parts. What we do is the respective node covers the communication facilitated by the DS nodes, and the ultimate parts comprise eliminating the repetitive DS nodes by covering the redundant parts within the network, facilitating the information flow across the system. The bidirectional network comprised the CCDS revolving around 7 rounds to complete the computation, facilitating communication. The maximum node degree within the network represented by delta requires the computation complexities for the various constituent aspects that are part of O delta square, and that are used for the relay node selection alongside the pruning phase. Finally, the computation complexity necessity for the fast CMDSM facilitates the exponential integer programming for the branch and cut algorithms. So coming to the final results, the technique suggested for IoBT networks aid in detecting the topology of strategically positioned nodes, reducing the dominant set sizes, or as they are called DS. The CIPCI centrality assists in measuring the node's identification within the set's characteristics. The suggested CCDS technique assists in computing the minimal dominant set, or MDS, using integer programming with the CDS construction element involving the DS computation from the minute per node constituent nodes in a 2-hop neighborhood. The fast CMDSM algorithm facilitates the computation of MDS by exponential integer programming for the branch and cut algorithms. And the findings of this study, basically my research, indicates that the proposed models and algorithms for IoBT networks effectively deliver robust and cost-effective network infrastructures, and at the same time provide ample security to the network so that things do not go haywire during the time of a war, or during the time when soldiers are supposed to communicate to each other in a warlike situation. The models and algorithms that we have come up with in our research help form a foundation for configuring the IoBT network design for continually changing missions, detect the topology of strategically positioned nodes, and calculate the minimal dominating set, MDS, as it is referred as. These models and algorithms contribute to the resilience of IoBT networks against cyber attacks and other unwanted actions. Also, touching briefly on the future research gap. So with this study, we now have a complete picture of the several models and algorithms deployed to defend IoBT networks against assault. However, more research is needed in several areas to guarantee this network safety. First, further study is required to design trustworthy protocols for IoBT networks that includes routing, authentication, and access management. These protocols and procedures must be reliable and quick to react to protect networks from cyber attacks and criminal activity. Second, there is a need for additional study into the construction of secure data storage and transmission methods for IoBT networks. These protocols should encrypt data at rest and transit across networks, Third, there must be a further study into creating safe hardware and software components for IoBT networks. These parts must have authentication and encryption capabilities to keep networks safe. Finally, more research is necessary to create a safe networking monitoring and management tools for IoBT system. This instrument must promptly identify malicious network activity and cyber attacks. So I'm concluding. So the military is a prime example of how technological progress has spurred the creation of new security measures for integrating disparate platforms. The military department experiences a challenge in the coordination through the various terrorists targeting their operations coordination. The Internet of Battlefield Things, or IoBT invention, has resulted in various benefits in securing data transmission through the various battlefield in real time. The technological innovation includes network models using stochastic geometry and heuristic algorithms in constructing the innovation. However, the stochastic geometry forms the basic unit structure alongside the mathematical computations included in the various layers of coordination exemplified by inter and intra layers. The internet connection facilitates technology coordination within the IoBT for secure data transmission. My recommendation would be that's pretty much what I covered. And basically, what we have done is reached uh, at a starting point from where we can go ahead and we can have more research connected to the frameworks, the algorithms, the networks, and how vastly, if it is spread, we need more data mechanisms and more entry points to entry and exit points to take care of the cyber security attacks that might be because of the terrorists that want to attack them, or even in a warlike situation, the other party might be looking at. Yes, I just covered this aspect as well. And then these are some of the sources that I have utilized during my research, during writing that paper. And thanks again for giving me an opportunity to present my paper. I'll stop sharing.